Welcome to Calc 2, Monday morning, April 13th. We have just a little bit left to talk about from chapter 11. We should finish it quickly and move on to chapter 12. But I want to talk a little bit about using some of the things we've learned. We've had sort of a whirlwind tour through series, infinite series, power series, Taylor series, Maclaurin series, and been stacking up a lot of things to think about, a lot of things to remember, a lot of things to use, but we haven't really taken time to show some of the reasons why we care about infinite series. And, if we were meeting face to face, we'd work through a few examples. We do have got a couple of weeks left, and so we can't take too much time, but I thought I would take just a little bit to show you some of the ways that the things we've talked about, power series and Taylor series, the way that the things they can do for us, the reason why we study them. Remember, I shared with you that they were developed a couple hundred years ago just to help with arithmetic. And we don't really need arithmetic help anymore. Our calculators are super powerful. But they've stuck around because there are things that we can use them for that the original founders, Taylor and Maclaurin and others, had never really dreamed about. And so I thought I'd talk about a few of those things. And I'm going to use two examples that we worked out to help us, two separate examples. So one of them is the power series for 1 over 1 plus x, a video I posted. I did, not the calculus professor, on section 2. We dug into some of these things, and there's a result. And notice that the function 1 over 1 plus x has a power series that converges to it as long as x is between -1 and 1. If we're outside that interval, it diverges, it's meaningless. We have to make sure that x is between -1 and 1. And then we get a super nice way to write that infinite series. It's just the function 1 over 1 plus x. So for example, you could pick a number between -1 and 1, plug it in on both sides. Let's say we pick a half, and you would have a particular infinite series on the right. All the x's are gone, replaced with 1/2. And you would have a number on the left, 1 over 1 plus 1/2. And we would have a fact then that that particular series converges to that particular number, and it works for all values between -1 and 1. The second example we'll take a look at comes from the Maclaurin series for e to the x. Again, we worked that out in the video that I posted on section 2. And you can see the form we got there, x to the k over k factorial. And the nice thing about that one is it converges for all x. You can pick any number whatsoever, plug it in on the left, plug it in on the right, and you get a particular series that converges to that particular number. And so I want to just do a couple of examples that show you how these things can get used. And along the way, we're going to learn a couple of things that are in section 2 that I didn't have time to get to in that video. And when I post homework today, it will include some of the things that we talked about in that video, plus the things we're going to add to it today. So I want to start with the first one, this one right here, and I want to just do a few things. I showed in the video that we can differentiate or integrate a power series, and the series we get, integrating or differentiating term by term, converges to the function that we get, which is either the derivative or the antiderivative, whichever one we happen to do. And there are other things that we can do. For example, so let's try this problem. Find a power series for the function equals 1 over 1 plus 2x. So we're just going to double our x value before we do the arithmetic. And if you think about it, if we give this function a name, since I call this one f, let's call this one g. This function is simply this function composed with the doubling function. Okay? And so because we can see this function playing a role in how this function is calculated, we can use this power series. In fact, we have to do two things. The first thing we have to do is replace all of the x's with 2x. So we're going to think this function evaluated at 2x. That's how we get to this function. So let's do that. Replace all the x's, and I'll write equals. The same as this equals sign, we're finding a power series for it, and nothing changes here. And when I replace x with 2x, I get a 2x, and then I get a 2x squared over 2. Oh, I'm looking at the wrong series. Should be minus. We're looking up here, and then we're going to square it. And then we're going to subtract off Monday morning, 2x cubed, and so on. And if we want to, we can do the arithmetic. You can just see the coefficient doubles on every, as we move down the terms. Okay, the other thing, that's the first thing, replace x with 2x, compose this function with the doubling function. The other thing is to find the interval. That is, when I replace x with 2x, I probably have affected this interval. Well, we know that whatever we plug in here, it's got to be between -1 and 1. If I plug in 2x, then I need to ensure that that is always between -1 and 1. So we get a meaningful statement, it converges. And then we can just solve that inequality for x. It's easy to do, divide by 2. And so we see what plugging the 2 in there, what it does is it affects the radius of convergence. In particular, it cuts it in half. So for this power series, it converges to this function, but it only does it inside -1/2 to 1/2. It just makes sense. If we speed our x's up by doubling them, we cut the interval down by halving it, and so on. So I can take what I know here, I can find a power series form for that function, 1/1 plus 2x, and I didn't have to work very hard. I could use, the hard work's embedded right here in this result. And so we get the result nice and easy. Okay. That's another modification. Again, I mentioned in the previous video, I said there were two things we could do: differentiate, integrate, and now there's a third one. We can compose them. And I think we can generalize this to any kind of linear function. We don't want to get too exotic with this composition. But here's another one we can do, which is not linear. And that is, I would like to find a power series for 1/1 plus x squared. So let's try the same thing. This is that function composed with the squaring function. So let's think of our power series that way. Wherever the x's show up, we're going to plug in x squared. So I get 1 minus x squared plus x squared squared. We're slipping an x squared in for this x, and then squaring minus x squared cubed, and so on. Clean that up. And you can see we just hit the even powers now. We've managed to avoid the odd ones. But remember, it doesn't converge everywhere. Only the thing that we're plugging in this case, x squared, has to be between -1 and 1. Okay, because of the square, maybe it's a little trickier to solve than this one was with just a double in there. But think about it. What kind of numbers squared lie between -1 and 1? And you should be able, not so much actually solving the inequality, but just by thinking about it. Well, if x is between -1 and 1, then so is x squared. If x is outside 1 or -1 and you square it, we're still outside -1. So we see the same interval is going to work. for all of these x's, this is true, and therefore that is true. Okay? So another one. Again, we started with one we knew, we'd established before. We were able to slightly modify it to come up with a power series for this function, and then we did it again. Power series for that one. And now things get kind of halfway interesting. Let's integrate the thing we learned in that previous video. So here is a function, here is its power series, and on the interval of convergence, we can integrate, and we get convergence still. So the antiderivative of this function, we all know, is the inverse tangent of x. And if you integrate on the right, we're going to get x minus 1/3 x cubed plus 1/5 x to the 5th, so on. And when we integrate, the radius stays the same. We could gain an endpoint, and we do. When x is plus 1, we get an alternating series, 1 minus 1/3 plus 1/5. The terms go to 0, they decrease uniformly, so we get convergence at 1. And now I want to investigate what happens at x equals 1. It's sort of the whole point of following this line of thought. If x equals 1, I get the inverse. Remember, for all of these x's, we get a true statement here. So I get the inverse tangent of 1 equals 1 minus 1/3 plus 1/5 minus 1/7, so on. Now it's kind of like the alternating harmonic, except it skips the even numbers. And now, what is the inverse tangent of 1? The angle whose tangent is 1, we all know, pi/4. So I get this alternating, almost harmonic series converges to pi/4. Now let's multiply by 4. And I get an infinite series that converges to pi. Okay. Because you're in Calc 2, you probably know pi is an irrational number, and for some reason, I'm not quite sure what, but there are people, maybe you are one of them, that really love to memorize pi to however many digits they can, 50 or 100 or 200. Of course, the sequence goes on and on, never repeats. But how do we know the digits of pi? We can use this series. That is, this series converges to pi. If I want to get closer and closer to the real value of pi, all I have to do is add enough terms here. And so if I want to know the first 100 digits of pi, good morning, William.
Good morning.
I'm recording a lecture. You can listen in before I open up my office hours. So I'll let you listen in and we'll finish this and then we'll have office hours, okay?
Okay, sorry, I just realized I'm a bit early.
Oh, no problem. It gives me an audience. That'll help. So we can use this infinite series to get as close to pi as we want. If you want 1,000 digits, you just need to include enough terms here. And notice all we have to do over here is simple arithmetic. Add, subtract, and divide. That's it. Now, it turns out that this series converged to pi fairly slowly. And so people that really care about approximating pi to any number of digits, they've been able to find series that converge to pi just like this one does, but they converge much more rapidly. So this is not the actual one they used, but you can see the concept and how we can use the simple arithmetic to get us information about an irrational number like pi, and we can do it for lots of different numbers. All right, that's what I wanted to show about this function. Now let's take a look at e to the x. So I teach probability theory, and in probability theory, we learned that there is a function, super important. It's, I'll call it math, e to the minus x squared. So you've probably heard about, and maybe you've asked a teacher, do you grade on the normal curve? Well, the normal curve referred to is this function right here. Now, it's translated, maybe to, this one is symmetric around 0, and maybe the normal curve, you want it to be symmetric around an exam average, so 75. So you just have to do some simple algebraic translations to this curve. But if you strip all that extra stuff out of it, this is the function who's referred to when we think about a normal curve, or maybe, in general, just about normal distributions. This is the function. And in probability theory, we need to integrate it. That is, we need to find areas under the curve, because areas under the curve correspond to the probabilities of certain events happening. The trouble is, this is one of those functions. The fundamental theorem, it's continuous, so the fundamental theorems guarantee it has an antiderivative, but it is impossible to write its antiderivative in terms of the function we use. It's a proven fact. It's not like no one's found it yet, everybody's looking. It's a proven fact. It's impossible. So if I'm going to try to use the fundamental theorem, I can't. I strike out, because the fundamental, to find area under the curve, I need an antiderivative, and there is no antiderivative. So what can we do about that? Well, we can find a series that converges to it, and a power series, and we have one on the board over here. They're super easy to integrate. So just like we did before, I need to convert this one, and here we have the luxury of not having to worry about where it converges like we had to worry about for this one. We can do whatever, and it's going to converge everywhere. So what I'm going to do is evaluate this function at minus x squared. That is, this is the composition of e to the x and the function negative x squared. And the way we do that is wherever x shows up, we just plug in minus x squared. So here we go. Let me start a new line. I get 1, and then I get minus x squared. And then I get plus 1/2. And then we plug in minus x squared, and we square it. And then we get 1/3 factorial. We plug in minus x squared, and we cube it. And now let's clean that up. You can see we get an alternating series. 1/3 factorial, that's 6. Oops. This should be plus, and this one should be minus. Even power, odd power, so on. And that converges to e to the minus x squared for every x value. For every x, minus infinity to infinity. So now if I want an antiderivative of this function, as on its own, as is, it's impossible, but now it's nice and easy. I just integrate these terms of the power series, and I can't do all of them, but we can do enough that we can get the antiderivative super accurately. So we just include enough terms that we feel like we've captured the antiderivative e to the minus x squared. So we turn an impossible problem into an easy problem algebraically, and the question then becomes like how many terms, and that's really not a Calc 2 subject, so we'll just leave it there. All right, so there are a couple of reasons where we could use power series, Maclaurin-Taylor series, to help us solve particular kinds of problems. In section 4, there may be a few other things there. If it doesn't show up on the assignment that I make, then we're not going to worry about the other things that are presented in section 4. There's one more thing I want to talk about. Just you'll see it in the homework. So let's go back to the first example. We had 1/1 plus x. The power series for it was, let me see, 1 minus x plus x squared minus x cubed. And now I want to find a power series for, let's say, x squared over 1 plus x. So I'm going to think about that as x squared times 1 over 1 plus x. So separate this out, and then I get this function whose power series I know. So I realize all I have to do is get the power series for this guy and multiply by x squared. That is, raise all the powers by 2. So 1 turns into x squared, x turns into x cubed, x squared turns into x to the 4th, and so on. And that all works on -1 to 1. We didn't do anything to change the interval, so it inherits. I should have written it up here. All right, so that concludes what I want to do out of section 4. I'll post an assignment, and then the next thing we're going to do is move on to chapter 12, which is another sort of radically different topic. So